Moving forward, we're going to be welcoming to the stage the George Mason University team. This team is led by Sherwin, and he's going to be presenting on developing stormwater for resilient Old Havana through the use of green infrastructure.
Hello. Hello, everyone. I am Sherman Zahira. I am a graduate student in Environmental and Water Resources Engineering at George Mason University, and I will be presenting on how to develop a flood-resilient Havana. Are green infrastructure practices feasible? To give an outline of my presentation, I will give an introduction to the study subject, my methodology for tackling this problem, and the results I came up with, and future objectives. So, from recorded history up until now, Havana and Cuba as a whole has been victim to several significant flood events. Irma, Alberto, there was a recent tornado a couple months ago that all bring about heavy flooding. And this flooding causes a lot of infrastructure damage as well as harm to life and people. And as a result, significant economic damage and infrastructural. So the objective of the study is to evaluate the potential of green infrastructure implementation within Old Havana to reduce the quantity of stormwater runoff. To give a basic hydrology background, urbanization is directly correlated to an increase in stormwater runoff, and this runoff leads to increased flooding and pollutant loads. If you look at this diagram, you see in natural ground cover, meaning there's been no development on it, 50% of the water gets soaked into the ground, 40% of it evaporates back into the air, and 10% becomes runoff. But when we urbanize an area, there's nowhere for that water to permeate into the ground. So therefore, most of that water becomes runoff. And we quantify the surface runoff through something known as a rational method, it being the product of the rainfall amount, a land use coefficient, which is dependent on the type of ground that our rainfall is hitting on, and the area of interest. In addition to rainfall, we also have storm surge, which also presents heavy damages to coastal communities. And this is a result, this is due to water rise from air forcings due to hurricanes, in addition to current tidal situations, as we see through this diagram. And storm surge usually will go over seawalls and barriers and inundate buildings and a large area of Havana. Climate change is predicted to increase both the rainfall intensity and frequency in these high-intensity storm events. And current infrastructure right now is not resilient to these storm events. Resiliency meaning the infrastructure and the community's ability to bounce back as a result of a storm and reduce financial, economic, and financial, infrastructural, and life risk. So there's a necessity to adapt to this predicted increase in rainfall intensity and frequency. And in order to do this, I propose implementing more green infrastructure initiatives. As you can see through this diagram, there's a hydrograph that depicts post-development conditions. We see the high peak flow as well as at a shorter time, meaning more flash flooding, as compared to pre-development where we get lower peak flow and further time to that peak flow. And traditional methods reduce the stormwater quantity, but still more flooding occurs. So the goal is to use green infrastructure initiatives to reduce the amount of volume and the time that it takes to achieve this peak flow. Green infrastructure has been heavily implemented into developed countries, the United States, Europe, but it has not seen much implementation yet in developing countries. And for this study, according to as said by the World Bank, Cuba will be considered a developing country. I found two studies that studied the potential of green infrastructure in developing communities, one for Tanzania in Africa and one for Peru. And the main point that those studies portrayed is that it is necessary to adapt green infrastructure development practices for varying cultures, economies, and technical capabilities. The engineers over there don't have as much resources, technical and financial, to develop the green infrastructure initiatives that we do in more developed countries. So being able to adapt for these developing countries is an absolute necessity. The types of green infrastructure methods that I will be discussing are green roofs, bioretention cells, also known as rain gardens, permeable pavement, rainwater harvesting, and natural shorelines. The study site that I will be looking into is Old Havana, a 1.60 square mile municipality within Havana that was settled back in 1519. And it holds significant cultural and historical value. So the goal is to be able to make Old Havana more resilient, more sustainable, while maintaining its cultural integrity. The model I used for this study is a SWIM 5 developed by the United States Environmental Protection Agency, and it uses inputs such as rainfall, land cover, and watershed characteristics to model the study site's hydrology. There is currently no freely available live rainfall data for Havana, and a study that I came across used a storm recorded at the Miami International Airport in 1979, and through various statistical analysis, we can use that design storm as the 100-year design storm, which is typically used for engineering analysis. And by 100-year design storm, that means a storm that has 1% chance of occurring every year. In addition, a climate adaptation tool was used within the study to develop a predicted design storm for 2079, given the predicted increased rainfall. So if you look at this hydrograph, we can compare the rainfall amount per hour for the design storm, and we see a 17%, by looking at the peak value, we see a 17% increase in rainfall quantity within, between the current design storm and the 2079 predicted storm. So, and this hydrograph used for the entirety of Old Havana, comparing the current design storm and the 2079 predicted storm, we see a 35% increase due to climate change and surface runoff. Drainage conditions using visual analysis, the current percentage of imperviousness within Old Havana was considered to be 90%, and my goal is to reduce this to 45% as a whole using green infrastructure. And by comparing the present, for the current design storm, if I implement that 45% of green infrastructure, we see a 27% decrease in runoff due to the implementation. So what I did is, using Google Maps to look at various areas within Old Havana, I located several areas where I believe, through an engineering and landscape architect point of view, that these initiatives can be implemented. And then within that site, I used SWIM to model the runoff changes, as well as using an LID cost tool by the Water Environmental Research Foundation to determine the cost of implementing those proposals. So the first method I'll be talking about is a bioretention cell, as we see here. And how these work is that rainwater goes into this garden and infiltrates within the soil and the planting, and instead of turning into runoff, it recharges groundwater, and then that extra runoff that the groundwater can't hold gets released into the storm sewer system. So, and here we have Plaza Vieja. I determined a study site area of 45,000 square feet with the 2 black circles representing 2 bioretention cells. And by implementing these 2 bioretention cells, we get a 30% decrease in runoff. Within these hydrographs, please ignore the stepwise motion of the current conditions. It's something with the Swim 5 software that I couldn't fix, but if the peak value still holds for comparison. For the 2 cells, we get a $4,600,000 cost with a $160 per year maintenance cost. So over 50 years, we get a $59,000 cost, with the benefits being reduced stormwater runoff, increased better water quality, as well as an increase in aesthetic to the plaza. A lot of green infrastructure isn't meant just to mitigate stormwater effects, but to add aesthetic value to the area of interest. My second proposal is permeable pavement, as we see here. It looks a lot like your standard pavement, but instead of water turning into runoff, it infiltrates within the pavement through the layers and recharges the groundwater, and with the extra draining into a stormwater system. Looking at Plaza de la Catedral, we have an area of 13,250 square feet with 100% imperviousness. And to replace all that with permeable pavement, we get a 70% reduction in runoff volume. This costing $17,500 with an annual maintenance cost of $250 per year, totaling over a 50-year period, $24,000, with benefits being mitigated flooding. Green roofs, what these is rather than having typical roofing for a building, it's more vegetated roofing. And what this does is it captures stormwater, and it also provides insulation to the building, which reduces energy costs, and as well as providing an aesthetic value to the roofing of a building. This has been used in many hospitals, like I proposed here, where the patients can go out and enjoy the green scenery. So by implementing the Swim 5 model, we get a 60% reduction in runoff volume. With a large cost of $500,000 and a $1,400 annual cost, totaling $662,000 over a 50-year period, with benefits being mitigated flooding, reduced energy consumption within the hospital, as well as an increase in the well-being of the ambience of the hospital. Rainwater harvesting, using cisterns and barrels to capture rainwater. To connect to a building, I connected to the hospital previously mentioned, and to capture a 2-year storm off the roof, I had to develop a 16,000 liter gallon with an estimated cost to implement of $47,000. And Havana currently struggles with water availability, so this would be able to use water to capture for gray water purposes, leaving more for drinking. Natural shorelines, like this one shown here, although I didn't model, are essential to protecting coastal communities from storm surge. As storm surges go into land, if we have these mangroves and wetlands, they provide friction to the storm surge, and then this, as a result, reduces the amount of height within the surge, which then reduces the amount of risk that a storm presents. El Malecon is an area with a seawall that hasn't shown to been resilient enough to storm surge events. So by adding this, adding natural shorelines there and restoring them, the seawall and the natural shorelines can work together to reduce the amount of stormwater surge, as well as contribute to a healthier ecosystem. So to conclude, green infrastructure has demonstrated to be an effective method for mitigating stormwater-related issues, and implementing them will increase resiliency to storm events. And these practices should be implemented through a long-term watershed management plan over the next several years as Havana continues to grow and redevelop, to slowly implement these plans, as well as to promote interdisciplinary collaboration between engineers, landscape architects, and stakeholders. Community involvement is essential, and to use public meetings and town halls to discuss ideas with the people and to promote volunteerism to involve community and reduce costs. Topics for future study include coastal storm surge modeling to exactly evaluate the amount of storm surge, water quality modeling, how to promote effective communication methods, and how to promote interdisciplinary practices to implement green infrastructures in developing communities. Thank you all for your time, and any questions?